Yo, today's integral really does look awesome. It's the integral from 0 to infinity of natural log x divided by 1 plus e to the x squared dx. So how exactly are we going to approach this? Well, my plan here is to evaluate a general case, and by general case I mean let's define an integral function in terms of some parameter s as the integral from 0 to infinity of x to the s minus 1 divided by 1 plus e to the x squared dx. So this will give us a nice generalized result in terms of a parameter, and this can solve our integral if we use Feynman's trick of differentiating under the integral sign. So differentiating with respect to the parameter s and switching up the order of the integration and differentiation operators, we now have the integral from 0 to infinity. And because of the switch up, this is now a partial derivative by the Leibniz rule, x to the s minus 1 divided by 1 plus e to the x squared dx. Now, differentiating partially with respect to s means that all the x terms are just constants. So what we get is the integral from 0 to infinity of 1 by 1 plus e to the x squared. And differentiating x to the s minus 1 with respect to s will give us the repeated function times the natural logarithm of this constant base x, constant in the s world anyway. So that's the derivative of I with respect to s. And notice that once we plug in s equal to 1, we get exactly what we need. We get our target integral. So that's the plan. We evaluate I of s, and we'll get a function of the parameter s, and we differentiate with respect to that parameter, and then plug in s equal to 1, and that solved the integration problem. Question is, how exactly do we evaluate I of s in the first place? The first thing I'd like to do is factor out an e to the x term from the denominator. So I can write this as x to the s minus 1 dx divided by pulling out this e to the x term. That leaves me with e to the negative x plus 1, and all of this is squared. And the reason for pulling out e to the x is not just to demonstrate my immaculate pullout game, which is of course an essential skill to have in mathematics as well, but the reason is something else. Let me show you exactly what I'm talking about. Applying the square will give us e to the 2x, and writing that in the numerator as x to the s minus 1 times e to the negative 2x divided by 1 plus e to the negative x squared dx. I now have something on which I can apply the geometric series expansion. So we know that the reciprocal of 1 plus x can be expanded as the sum over the non-negative integers k of negative 1 to the k times x to the k. And this is valid when the absolute value of x is less than 1. But here we have to replace x by e to the negative x, and on the interval from 0 to infinity, e to the negative x is indeed less than 1. So we can expand this as the sum over k of negative 1 to the k times e to the negative kx. Okay, but the problem is this is not exactly what we have in our integrand. Well, we do have it, but a derivative of it. What am I trying to say? Let me just change the appearance of the integrand a bit. So let me write this as the integral from 0 to infinity of x to the s minus 1 times e to the negative x times e to the negative x divided by 1 plus e to the negative x squared dx. And this structure is something that's popped up quite a bit in my videos. And you can get this structure once you differentiate this geometric series with respect to x. So on differentiation, we get a negative 1 by 1 plus e to the negative x squared, and because of the chain rule, we have a negative e to the negative x term as well, so that sorts out to e to the negative x. And on the right-hand side, we have the sum over k of negative 1 to the k times negative k to the negative k times e to the negative kx. And negative k is just k times negative 1, so we can absorb a negative 1 over here. Okay, so that's the required series expansion, but note something here, that for the k equal to 0 term, you get a 0 because k is being multiplied now. So we can start this sum at 1. So this implies that I of s equals the integral from 0 to infinity of, wait, let me just write this down here for some more space. So we can write this as the integral from 0 to infinity of x to the s minus 1 times e to the negative x times the sum over the positive integers k of negative 1 to the k plus 1 times k times e to the negative kx, integration with respect to x. And because these two are independent of the index variable k, we can slip them inside the summation operator. And that immaculate slip-in means we're ready for round 2. So we have the integral from 0 to infinity of the sum over k of negative 1 to the k plus 1 times k times x to the s minus 1 times e to the negative k plus 1 x, where I've just multiplied the two exponential functions there. So that's I of s so far. Next up, let's switch up the order of the integration and summation operators. So we have the sum over k of the integrals from 0 to infinity of negative 1 to the k plus 1 times k. And because these two are independent of the x variable with respect to which we're integrating, we could just write them outside the integration operator, showcasing once again our excellent pull-out game. Yeah, the pull-out game is pretty strong with this integral. Anyway, so we have negative 1 to the k plus 1 times k, and the integrand is x to the s minus 1 times e to the negative k plus 1x dx. And longtime viewers of the channel will recognize this as the perfect opportunity to apply the gamma function. But for that, we need a substitution. We're going to let k plus 1 times x equal to u, and this implies that dx equals du divided by k plus 1. So this implies that I of s equals the sum over k of negative 1 to the k plus 1 times k times the integral, still from 0 to infinity, the limits are clearly not bothered, of u to the s minus 1 divided by k plus 1 to the s minus 1 times e to the negative u du by k plus 1. Okay, so again, we have these k terms that are independent of the u variable. So we can write this as the sum over the positive integers k of negative 1 to the k plus 1 times k divided by k plus 1 to the s on their multiplication times the integral from 0 to infinity of u to the s minus 1 times e to the negative u du, which we recognize as our good friend, the gamma function evaluated at s. So this implies that I of s equals gamma s times the sum over the positive integers k of negative 1 to the k plus 1 times k divided by k plus 1 to the s. Now, how exactly do we translate the structure, the summation that is, into something more familiar? Allow me to make a transformation of the index variable. So we have k plus 1 equaling n. So this implies that I of s equals gamma s times the sum over n now, starting at 2, of negative 1 to the n times n minus 1 divided by n to the s. So this means we have gamma s times the sum over n of negative 1 to the n times n divided by n to the s. So of course you can write this as n to the s minus 1 in the denominator minus the sum over n of negative 1 to the n divided by n to the s. And now to get something even more familiar, I'm going to introduce a couple of extra negative signs and absorb them into the negative ones. So what we have here are sums related to the Dirichlet eta function. So eta s is defined as the sum over the positive integers n of negative 1 to the n plus 1 divided by n to the s. But our sums are starting at 2. But for the case of k equal to 1, we're going to have negative 1 squared, which is just 1, and 1 to the s, which is 1. So that means these are just the eta functions minus 1. So all of this implies that I of s equals gamma s times negative sign eta s minus 1 plus 1 now plus eta, no wait, plus eta s minus 1, some nice cancellation here. And we have this beautiful structure here. This is a very nice integral in itself, besides the target integral, that is. So we had this thing in the denominator, and we have this beautiful generalized result. It's gamma s times eta s minus eta s minus 1. And now to get our target integral, this is, of course, I of s, differentiating under the integral sign, gives us the integral from 0 to infinity of x to the s minus 1 times log x. So we just want to plug in s equal to 1 anyway. So we have log x divided by 1 plus e to the x squared. And this equals, differentiating now the right-hand side, gives us gamma prime s times eta s minus 1. And let me just give myself some more writing space. Plus gamma s times eta prime s minus eta prime s minus 1. And wait, I had to plug in s equal to 1. So that means I have gamma prime 1, eta 1, eta 0, and of course I have the derivatives here as well. Okay, cool. Okay, so here's a breakdown of all the values you're going to need. Gamma 1 is just 0 factorial, which is 1. Then you have eta 1, and eta 1 is log 2. And eta 0, defined using analytic continuation, is 1/2. As far as the derivatives are concerned, gamma prime 1 equals negative Euler-Mascheroni constant. I have an Instagram write-up on important derivatives of the gamma function. You can check that out using the link provided in the description box. And eta prime at 1 is something I've evaluated as part of the evaluation of another cool integral, link again in the description. And this is Euler-Mascheroni constant times log 2 minus log square 2 by 2. And I know those watching are praying that the Euler-Mascheroni constant somehow stays as part of the final solution. And eta prime at 0 deserves a video of its own. And this equals 1/2 times the logarithm of pi by 2. So yeah, it looks like we're going to get a really exotic result. So this implies that our target integral I equals negative Euler-Mascheroni constant log 2 over here minus eta 0 is 1/2 plus gamma 1 is 1. Then we have Euler-Mascheroni log 2 minus log square 2 by 2 minus 1/2 of log pi by 2. Okay, so we see that we're going to lose this term. But that's all right, because we still have 1/2 of the Euler-Mascheroni constant. That feels good. Minus 1/2 of log pi by 2 minus 1/2 of log square 2 by, terribly sorry about that, log square 2 by 2. So we can factor out a factor of 1/2. We have Euler-Mascheroni constant minus log pi minus squared logarithm of 2. And if you're wondering where did that log pi by 2 go, well, I just decomposed it into log pi and minus log 2, but we have two negative signs here. So yeah, I'm going to have plus log 2. And the Euler-Mascheroni constant can be written as log e to the Euler-Mascheroni constant, which just looks amazing, by the way. I mean, you have one of Euler's constants to another Euler's constant. That's really cool. So we have 1/2 of the difference of logarithms can be written as the logarithm of the fraction. And we have this log 2 as well, so we can write that as part of a product. We have log 2 times e to the Euler-Mascheroni constant divided by pi. That looks just gorgeous. Minus the squared logarithm of 2. And that is a beautiful looking integration result. Definitely one of my favorites so far. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.